Picture this: two immense cosmic islands, each home to hundreds of billions of stars drifting silently through the void. They've been on this path for millions, even billions of years, drawn together by the invisible threads of gravity. And then collision, not with a crash, but with a slow, inevitable embrace that reshapes everything in its wake. This isn't the stuff of blockbuster movies. It's happening right now in the depths of space, and the consequences are more astonishing than anything we could dream up. What unfolds when galaxies merge? It's a question that sounds almost poetic, but the reality is a spectacle of chaos and creation. These collisions don't just rearrange stars, they spark explosions of new life, twist the fabric of spacetime, and awaken dormant giants lurking at galactic hearts. Imagine entire solar systems flung into new orbits, stars born in fiery bursts, and supermassive black holes locked in a gravitational tango. The universe doesn't just survive these mergers, it thrives, transforming in ways that challenge everything we thought we knew about cosmic evolution. And here's the most mind-bending part. We're part of this story too. Our own Milky Way is on a collision course with the Andromeda galaxy, a slow-motion dance that will reshape our night sky in ways we can barely fathom. But long before that distant future, galaxies across the cosmos are already merging, rewriting their destinies in real time. So join me as we peel back the layers of these interstellar encounters, uncovering the hidden forces at work and the breathtaking beauty they leave behind. This is a journey through the most dramatic events in the universe, where destruction and creation collide, and where the cosmos reveals its endless capacity for reinvention. The vast emptiness of space might make galaxies seem isolated, but they're constantly moving, pulled by gravity's invisible hand. When two galaxies draw near, their dance begins, not with a violent impact, but with a gravitational whisper that slowly reshapes them both. Think of it like two great whirlpools in a cosmic ocean, their currents intertwining over eons. The stars inside are so far apart that they almost never collide, but the delicate clouds of gas and dust between them, that's where the real drama unfolds. As the galaxies spiral closer, their outer arms stretch like taffy, pulled by tidal forces into long, shimmering streams of stars. These graceful arcs, called tidal tails, can stretch for hundreds of thousands of light years, glowing with newborn stars ignited by the collision's shockwaves. Meanwhile, the galaxies, dark matter halos, the mysterious invisible scaffolding that holds them together, begin to merge, warping the very fabric of space around them. It's a transformation so profound that the original spirals may never look the same again. Some emerge as elliptical galaxies, smooth and featureless, while others become chaotic, star-forming powerhouses. But the most astonishing part, these mergers aren't destructive, they're creative. The violent compression of gas clouds triggers bursts of starbirth, lighting up the galaxies like fireworks. Supermassive black holes at their centers awaken from dormancy, feeding on the chaos and shooting out jets of energy visible across the universe. Even our own Milky Way bears the scars of past mergers, with streams of ancient stars telling the story of galaxies long absorbed. This relentless cycle of collision and rebirth is how galaxies grow, evolve, and ultimately, how the universe writes its own epic history. When galaxies collide, it's the gas between the stars that feels the fireworks first. Picture two vast collections of interstellar clouds, each one a nursery for future stars, suddenly squeezed together by the gravitational tides of merging galaxies. This cosmic pressure cooker triggers something extraordinary, a starburst. These aren't just ordinary regions of star formation. In a starburst galaxy, the rate of star birth skyrockets, with hundreds or even thousands of new stars igniting every year, compared to our Milky Way's more modest pace of just one or two. Take the antennae galaxies, a pair of spirals locked in a slow-motion collision. Their tangled arms are studded with brilliant blue clusters, each one a family of stars younger than 10 million years, mere infants on the cosmic timescale. These clusters glow with the intensity of millions of suns, their light so fierce it outshines entire galaxies. But here's the twist: starbursts are fleeting. Like a match struck in a windstorm, they blaze intensely but burn out quickly. The very process that creates them, the compression of gas, also sows the seeds of their demise. As newborn stars ignite, their fierce radiation and powerful stellar winds blast away the remaining gas, starving future generations of star formation. Yet in their brief lives, these stellar fireworks leave an indelible mark. The hottest, most massive stars live fast and die young, exploding as supernovae that enrich the galaxy with heavy elements, the building blocks of planets and ultimately life. Meanwhile, the smaller, longer-lived stars become part of the galaxy's new backbone, their light blending into the collective glow of the merged system. It's a cycle of furious creation and quiet transformation, proving that even in the chaos of collision, the universe finds a way to turn destruction into something luminous. While the starbursts light up the outer regions of merging galaxies, an even more titanic battle unfolds at their cores, where supermassive black holes, each weighing millions or even billions of times the mass of our sun, begin their fatal dance. These cosmic behemoths, once the quiet rulers of their respective galaxies, are stirred awake by the chaos of collision. Drawn together by gravity, they spiral inward, carving swirling paths through clouds of gas and stars, their immense gravity warping space itself. This isn't just a slow crawl, it's a dramatic showdown. As the black holes close in, they whip surrounding matter into frenzied orbits, heating it to millions of degrees until it glows brighter than all the stars in the galaxy combined. These active galactic nuclei can outshine entire galaxies for millions of years, their brilliant jets of energy visible across the universe. But the real spectacle happens when the black holes finally meet. Locked in a gravitational embrace, they ripple spacetime itself, sending out waves, gravitational waves, that travel at the speed of light, carrying echoes of the collision across the cosmos. Sometimes the two black holes merge into a single, even more monstrous singularity. Other times, something far stranger happens. If the merger isn't perfectly symmetrical, the newly formed black hole can be kicked away at incredible speeds, an event astronomers call a black hole recoil. Imagine a cosmic cannon firing a supermassive black hole out of its own galaxy, doomed to wander the void between galaxies forever. These runaway black holes are rare, but when they occur, they leave behind a disrupted galactic core, a ghostly fingerprint of the violent encounter. Yet even in their absence, their legacy remains. The gravitational turmoil of their duel reshapes the galaxy's center, flinging stars into chaotic new orbits and altering the fate of everything nearby. Some galaxies end up with naked cores stripped of gas and dust, leaving behind a quiet, aging stellar population. Others become breeding grounds for new activity, as fresh gas spirals in to reignite the central black hole. These duels don't just change galaxies, they redefine them, proving that even the darkest, most invisible forces in the universe can leave the marks. While the most dramatic galactic collisions involve spirals of similar size smashing together in bursts of star formation, the universe has a quieter, more methodical way of reshaping itself, through galactic cannibalism. Imagine a cosmic food chain where the largest galaxies grow even more massive by steadily consuming their smaller neighbors. These so-called minor mergers might lack the fireworks of two giant spirals colliding, but their effects are just as profound, rewriting galactic histories one silent bite at a time. Take our own Milky Way. It might seem like a stable, solitary island of stars, but it's actually a cosmic predator with a long history of absorbing smaller galaxies. Scattered across our galaxy's halo are the ghostly remains of dwarf galaxies it has devoured over billions of years. One of the most famous is the Sagittarius dwarf spheroidal, a tiny galaxy caught in the Milky Way's gravitational grip. As we speak, it's being torn apart, its stars strewn across our skies in vast, faint streams, like glitter spilled across black velvet. Another casualty, the Enceladus galaxy, met its end nearly 10 billion years ago, but its stars still orbit within us, their chemical fingerprints revealing their foreign origins. These mergers aren't quick, violent affairs. They're slow, almost graceful processes where gravity does the heavy lifting. A dwarf galaxy might orbit its larger neighbor for billions of years, each pass stripping away more stars and gas until nothing remains but a delicate stellar stream. Unlike major mergers that ignite starbursts and awaken black holes, minor mergers are stealthy, reshaping galaxies without the fanfare. The larger galaxy doesn't erupt in chaos. It simply grows, its outer halo thickening with stolen stars. Yet these quiet takeovers leave unmistakable clues. Astronomers hunt for these cosmic fossils, oddly grouped stars moving in unison, or ancient globular clusters with strange orbits that betray their alien origins. Even our sun might owe its existence to one of these mergers, as the influx of fresh gas from a consumed dwarf could have triggered the birth of new stars, including our own. Galactic cannibalism isn't just destruction, it's renewal, a way for galaxies to recycle material and evolve without the drama of a head-on collision. And in the grand timeline of the universe, it's the most common way galaxies grow, one silent feast at a time. Spiral galaxies are cosmic masterpieces, graceful whirlpools of stars with delicate arms spinning through space. But when two spirals collide, something extraordinary happens. Their elegant structures vanish, replaced by something entirely different. The violence of the merger shakes them to their core, stripping away their distinctive features and leaving behind a smooth, almost shapeless giant, an elliptical galaxy. These cosmic blobs might lack the beauty of spirals, but they tell a story of transformation written in starlight. Picture a spiral galaxy's delicate disk, filled with swirling gas and young, blue stars. Now imagine the gravitational chaos of a merger sending shockwaves through that disk, throwing stars into chaotic new orbits. The one-sorterly rotation collapses into a jumbled, three-dimensional swarm where stars move in every direction like a hive of disoriented bees. Over time, the galaxy puffs up, its stars spreading out into a featureless cloud. The gas that once fueled star formation is either blown away by fierce stellar winds or devoured in one final burst of activity, leaving behind a population of aging, reddish stars. The result? A celestial fossil, a massive elliptical galaxy that may shine for billions of years but never again spark the birth of new stars. The universe's largest ellipticals didn't start this way. They grew through successive mergers, each collision adding more stars and erasing more structure. Take Messier 87, the colossal elliptical at the heart of the Virgo cluster. Its sheer size, trillions of stars, hints at a violent past, likely built from dozens of smaller galaxies consumed over eons. Even its infamous supermassive black hole, the first ever photographed, bears the scars of this history, weighing in at a staggering 6.5 billion solar masses, a monster forged by mergers. But here's the twist: not all mergers create perfect ellipticals. Some leave behind shell galaxies, where concentric ripples of stars, like the layers of an onion, reveal the aftermath of a spiral being torn apart. Others form ellipticals, a strange hybrid that hints at a spiral's lingering influence. These variations are cosmic fingerprints, each telling a slightly different story of collision and rebirth. What's truly humbling is realizing that our Milky Way may one day share this fate. When it merges with Andromeda in about 4 billion years, the two spirals will likely give birth to a new elliptical dubbed by astronomers. The familiar pinwheel of our night sky will vanish, replaced by a glowing, golden blob where new stars are rare, and the chaos of creation has settled into quiet old age. It's a reminder that even the grandest cosmic structures are fleeting, reshaped by the same forces that built them. Galaxies might look like collections of stars, But the real puppeteer behind their cosmic dance is something we can't even see: dark matter. This mysterious substance, invisible to telescopes and undetectable by light, holds galaxies together with its gravitational grip, shaping every merger in ways that defy intuition. Picture two galaxies approaching each other. Their luminous stars and glowing gas are just the tip of the iceberg, while beneath the surface, vast halos of dark matter stretch far beyond, dictating the terms of their collision. When galaxies merge, it's these dark matter halos that first interact, their immense gravity bending the paths of stars and gas like invisible hands sculpting cosmic clay. The outcome, whether galaxies spiral together in a slow tango or slam into a head-on crash, depends entirely on how these halos align. A glancing encounter might stretch a galaxy into long, starry ribbons, while a direct hit triggers a firestorm of newborn stars. Without dark matter's stabilizing influence, galaxies would fly apart, their stars scattered like sand in the wind. Instead, dark matter acts as the universe's ultimate glue, ensuring mergers leave behind something new rather than chaos. The proof is in the aftermath. Astronomers studying merged galaxies often find their stars moving in ways that defy the laws of visible matter alone. Orbits too fast, shapes too stable. Only dark matter's hidden scaffolding can explain it. Take the Bullet Cluster, where two galaxy clusters collided with such force that their gas clouds slammed together and slowed down, while their dark matter, unaffected by friction, raced ahead, leaving ghostly gravitational fingerprints in its wake. This cosmic sleight of hand revealed dark matter's presence more vividly than any telescope ever could. Yet dark matter's role doesn't end there. It shapes the universe on the grandest scales, weaving galaxies into vast filamentary networks where mergers are inevitable. Over billions of years, dark matter's pull herds galaxies into clusters, setting the stage for collisions that will birth even larger galaxies, each one a monument to the unseen force that built it. So while we marvel at the starbursts and black hole duels, remember, the true architect of these cosmic transformations works in the shadows, silent and invisible but undeniable in its power. One of the most breathtaking sights in the cosmos isn't a perfectly symmetrical spiral or a glowing nebula. It's the chaotic aftermath of a galactic collision, where gravity's artistry stretches entire galaxies into surreal, flowing shapes. When galaxies merge, they don't just bump into each other. They're stretched, twisted, and sculpted by tidal forces, leaving behind spectacular trails of stars and gas that can outshine the galaxies themselves. These luminous ribbons, known as tidal tails, are the universe's way of painting with gravity, a brushstroke that spans hundreds of thousands of light years. Take the Tadpole Galaxy, its name borrowed from the long, shimmering tail stretching behind it like a cosmic tadpole swimming through the void. That tail isn't just a pretty feature, it's a fossil record of violence. Every star in that luminous stream was once part of the galaxy's disk, ripped away by the gravitational tug-of-war between colliding galaxies. What's astonishing is how delicate the process can be. Despite the immense forces at play, stars themselves rarely collide. Instead, they're gently pulled from their orbits, like leaves caught in a slow-motion whirlwind, forming these ethereal bridges and tails that linger for hundreds of millions of years. But tails aren't the only structures born from these encounters. Sometimes, galaxies form vast bridges of gas and dust between them, cosmic lifelines where material flows from one to the other. The Mice galaxies, a pair of spirals in the midst of merging, showcase this beautifully. Their long, filamentary tails are already stretching away, while a thin bridge of newborn stars connects them, a temporary highway of light forged by the collision. These features aren't just debris. They're evidence of the universe's recycling program, where material stripped from one galaxy can become the building blocks for another. What's even more remarkable is how these tidal structures evolve. Over time, the stars in the tails burn out, leaving behind fainter, older stars that gradually disperse into intergalactic space. Some may even form rogue star clusters, isolated groups wandering the void, orphaned by the merger that birthed them. Meanwhile, the gas in these tails can collapse under its own gravity, sparking new bursts of star formation far from the galactic core. It's a reminder that even in destruction, the universe finds ways to create. These cosmic scars aren't just beautiful, they're vital clues for astronomers. By studying the shape and composition of tidal tails, scientists can reconstruct the merger's history, like detectives piecing together a crime scene. The angle of a tail reveals the trajectory of the collision, while its chemical makeup tells us what kind of material was stripped away. Some tails even contain globular clusters, dense knots of ancient stars that act as cosmic breadcrumbs, tracing the path of the galaxy's dance. And here's the wildest part: we might be living in the wake of such an event. The Milky Way's outer halo is littered with stellar streams, ghostly remnants of smaller galaxies torn apart by our galaxy's gravity. The stream, a vast arc of gas stretching across our sky, could be the shredded remains of a dwarf galaxy, its material slowly raining down onto our own. It's a humbling thought. Even our home galaxy is a product of mergers, its history written in the faint trails of stars we're only now beginning to map. These tidal tails and bridges aren't just distant curiosities, they're part of the story that shaped us, proof that even the grandest structures in the universe are never truly alone. Deep in the hearts of colliding galaxies, where supermassive black holes lurk, a celestial light switch sometimes flips on, transforming these dark monsters into the most luminous objects in the universe. We call them quasars, and their brilliance defies imagination. A single quasar can outshine an entire galaxy by 1,000 times, its light traveling billions of years to reach us. But what ignites these cosmic beacons? The answer lies in the chaos of galactic mergers, where gravity orchestrates a feast of epic proportions. When two galaxies collide, their swirling reservoirs of gas don't just form new stars. Some of it spirals inward, drawn by the immense pull of the central black holes. Imagine two whirlpools merging in a cosmic ocean, their currents funneling water toward a single drain. Now replace that water with gas clouds, heated to millions of degrees as they're compressed and accelerated to near-light speeds. By the time this superheated plasma nears the black hole's event horizon, it glows with such intensity that it can outshine every star in its host galaxy combined. That's the birth of a quasar, a gravitational powerhouse where a black hole's destructive appetite becomes the universe's spotlight. What's fascinating is how mergers solve one of astronomy's biggest puzzles: why quasars were so common in the early universe. Billions of years ago, galaxies were smaller, closer together, and constantly bumping into one another. Each collision was a potential quasar trigger, funneling fresh gas into waiting black holes and lighting up the cosmos like a city waking at dawn. Today, mergers are rarer, and quasars with them. Most supermassive black holes in modern galaxies sit quietly, their fuel exhausted or scattered, sleeping giants waiting for the next cosmic delivery of gas. But when they awaken, the spectacle is unmatched. Take the quasar Ton 618, so distant its light left when the universe was barely a tenth of its current age. Yet even now, its brilliance cuts across the cosmos, powered by a black hole weighing 66 billion suns, a monster likely grown fat from countless mergers. Or consider the Butterfly Galaxy, where two spirals are currently colliding, their central black holes not yet merged but already feasting on the influx of gas, their growing brightness a preview of the quasar to come. These brilliant beacons do more than dazzle, they shape their surroundings. Quasar winds can blast away a galaxy's remaining gas, halting star formation and effectively killing its host. It's a cosmic irony. The same process that fuels a quasar's fire also starves its galaxy's future. Yet without these eruptions, the universe might look very different. Quasars helped the early cosmos, their ultraviolet light breaking apart ancient hydrogen clouds and making the universe transparent to light. They're not just destroyers, they're pioneers, carving out the conditions for galaxies like ours to eventually form. So the next time you gaze at a distant quasar's pinpoint light, remember, you're seeing the aftermath of a galactic collision, a black hole's meal transformed into a lighthouse beam piercing the dark. These brilliant flares are fleeting by cosmic standards, lasting mere millions of years before their fuel runs dry. But for that brief, glorious moment, they dominate the cosmos, reminding us that even the darkest objects can become the universe's lights, if given the right gravitational nudge. Some galactic mergers don't follow the script. Forget orderly spirals transforming into smooth ellipticals. Imagine instead a cosmic demolition derby, where galaxies sideswipe each other, rebound, and leave behind a twisted wreckage of stars and gas. These are the universe's unfinished symphonies, collisions so chaotic they defy the usual rules, creating structures so bizarre they look more like abstract art than galaxies. Take NGC 7252, nicknamed the Atoms for Peace Galaxy. From a distance, it resembles a gigantic celestial explosion, with looping streams of stars arcing outward like debris from a detonation frozen in time. This isn't a single, clean merger. It's a messy, drawn-out affair where two galaxies have grazed past each other multiple times, their gravity yanking out immense tidal tails that haven't yet settled into anything recognizable. What makes these train wrecks so fascinating is their temporary nature. Most mergers eventually settle into a stable shape, but these fragmented galaxies are caught in the awkward in-between phase, cosmic teenagers, if you will, rebellious and unrefined. Their central regions might show signs of blending, with new stars forming from the chaos, while their outer regions remain stretched into wild, asymmetrical loops. The Atoms for Peace galaxy, for instance, has a core that's starting to resemble an elliptical galaxy, but its outskirts are a tangle of starry filaments, some stretching over 100,000 light-years into space. It's as if the galaxy can't decide what it wants to be when it grows up. Then there's NGC 6240, another cosmic oddball often called the Cocoon Galaxy. Here, two spirals have collided so violently that their gas clouds compressed into a frenzy of Starburst, lighting up the central region like a fireworks finale. Yet outside this brilliant core, the galaxy's original shapes are still visible, like two dancers mid-twirl, their arms interlaced but not yet merged. These systems challenge our assumptions about how quickly galaxies should evolve after a collision. Some take billions of years to settle, their stars wandering in chaotic orbits until gravity finally herds them into a new order. But perhaps the strangest wreckage of all comes from galaxies that don't fully merge at all. In rare cases, two galaxies can pass through each other like ghosts, their stars slipping past without collision, only for gravity to pull them back for another attempt millions of years later. These flyby encounters create fragmented, almost ghostly structures, galaxies with multiple nuclei, or ones that look like they've been turned inside out. The universe has no deadline for these transformations, and some galaxies may spend eons in this limbo, their fate undecided. What's remarkable is that even these chaotic mergers serve a purpose. The very disturbances that tear galaxies apart also redistribute their gas, triggering star formation and enriching the cosmos with heavier elements. The Atoms for Peace galaxy, for all its messiness, is a stellar nursery on a colossal scale, its loops glittering with young, blue star clusters. Even the ugliest cosmic train wrecks have beauty hidden in their chaos, proof that destruction and creation are two sides of the same galactic coin. And for astronomers, these fragmented systems are like puzzle boxes, offering clues about how gravity sculpts galaxies over time. After all, not every collision needs to end neatly. Sometimes the most interesting stories are the messy ones. When galaxies collide, the stars within them might glide past each other like ships in the night, but they're planets. That's a different story. Imagine a solar system like ours, with worlds orbiting steadily for billions of years, suddenly caught in the gravitational crossfire of two merging galaxies. The orderly dance of planets becomes chaos. Some are ripped from their stars entirely, condemned to wander the frigid void as rogue worlds. Others are flung into wild new orbits, tossed closer to their suns or hurled into the frozen outskirts. And a few. They might meet a far darker fate, spiraling toward the supermassive black hole at the galaxy's heart, where tidal forces stretch them into streams of molten debris. Consider what this means for Earth, or any planet nestled in a stable, life-friendly orbit. A galactic merger wouldn't just rearrange the stars in our sky, it could rewrite our solar system's entire future. Simulations show that as galaxies intertwine, the gravitational tug-of-war can destabilize planetary orbits, sometimes gently nudging them, other times catapulting them into oblivion. Even if our sun remains unscathed, Earth could be pushed into a colder, more distant orbit, turning our blue marble into an icebound wasteland. Or worse, if the Milky Way's central black hole grows restless during the merger, its gravitational reach could extend farther, snatching planets from their stars like a cosmic hand plucking fruit from a tree. Yet there's a strange silver lining to this upheaval. Some planets ejected into the darkness might carry life with them, insulated by subsurface oceans or thick atmospheres. These nomad worlds, untethered from any star, could drift between galaxies for eternity, their icy shells shielding microbial stowaways. And for those planets flung into orbits, they might find themselves in a Goldilocks zone around a different star, given a second chance at habitability. The universe has a way of repurposing chaos, turning destruction into opportunity, even for the smallest worlds. What's truly humbling is realizing how fragile our cosmic neighborhood really is. The same forces that built galaxies, the mergers, the collisions, could one day unravel the delicate balance that keeps Earth alive. Yet these events are also what make the universe dynamic, ever-changing, and ripe with possibility. For every planet lost, another might find its place in a new system, under a new sun, in a galaxy reborn from the wreckage of the old. It's a reminder that in the grand tapestry of the cosmos, even the most stable orbits are just temporary arrangements. Magnetic fields are the silent architects of galactic collisions, weaving invisible threads through the chaos and shaping outcomes in ways we're only beginning to understand. Picture a galaxy not just as a collection of stars and gas, but as a vast web of magnetic force lines, a cosmic fingerprint stretching far beyond its visible edges. When two galaxies collide, these fields don't just passively watch the show. They tangle, snap, and reorganize, becoming accelerators of chaos and directors of order all at once. Take the gas clouds caught in a merger's gravitational tides. Without magnetic fields, these clouds would simply collapse into stars or scatter into the void. But magnetism adds a twist. Like invisible rails guiding these fields channel turbulent gas into dense filaments, funneling material toward regions where star formation ignites. In the antennae galaxies, for example, astronomers have spotted magnetic fields aligning with the colossal bridges of gas stretching between the colliding spirals, proof that these forces are actively sculpting the merger's aftermath. The fields don't just respond to the chaos, they amplify it, turning diffuse gas into stellar nurseries at an astonishing rate. Yet magnetism's influence goes deeper. During a merger, the violent motion of charged particles, electrons and protons, can stretch and twist magnetic fields like taffy, amplifying their strength 1,000-fold. This creates feedback loops of energy, where turbulent gas strengthens the fields, which in turn stir the gas even more violently. It's a self-reinforcing cycle that can launch jets of material far beyond the galaxy, or compress gas so tightly that it sparks supermassive star clusters. In some mergers, these amplified fields become cosmic particle accelerators, whipping charged particles to near-light speeds and painting the sky with eerie synchrotron radiation. Light emitted not by stars, but by electrons spiraling around magnetic field lines. But here's the paradox. These same fields can also be suppressors. In galaxies like Centaurus A, where a past merger left behind a dusty, chaotic disk, magnetic fields act as brakes, slowing down the collapse of gas clouds and preventing them from forming stars too quickly. They're the universe's way of balancing the books, ensuring mergers don't burn through their fuel all at once. Without this magnetic regulation, galaxies might exhaust their gas in furious starbursts, leaving nothing for future generations of stars. The most breathtaking role magnetism plays, though, is in shaping the jets from supermassive black holes. As twin galaxies merge and their central black holes feast, magnetic fields coil around the infalling material like cosmic springs. When these springs snap, they launch jets of plasma hundreds of thousands of light years into space, beams so precise they could thread a needle across galactic distances. These jets, visible in radio telescopes as colossal lobes of energy, are sculpted entirely by magnetic forces, their paths carved by fields stronger than anything we could replicate on Earth. What's astonishing is how long these magnetic fingerprints linger. Long after a merger's fireworks fade, the realigned fields remain, frozen into the galaxy's new structure like scars. Some elliptical galaxies, the end products of violent collisions, still bear the imprint of their turbulent pasts in their magnetic maps, their fields tracing the ghosts of spiral arms long since erased. Even our own Milky Way's magnetic field might hold clues to ancient mergers, its subtle kinks and twists whispering stories of smaller galaxies consumed billions of years ago. So while gravity may be the star of the merger show, magnetism is the unseen choreographer, directing the flow of gas, tuning the tempo of starbirth, and leaving behind signatures that outlast even the stellar explosions. It's a reminder that the universe's most powerful forces often work in silence, hidden in plain sight, shaping the cosmos one collision at a time. Galaxies might seem like unstoppable engines of creation, forging stars at a furious pace during mergers, but the universe has a built-in off switch. This cosmic balancing act is called galactic feedback, and it's the reason galaxies don't burn through their fuel in one explosive burst. Imagine a star-forming frenzy so intense that it threatens to consume all the available gas, leaving nothing for future generations. That's where feedback steps in, acting like a celestial thermostat that keeps things from overheating. At the heart of this process are the very stars that mergers create. When massive stars ignite in starburst regions, they don't just shine, they scream. Their fierce ultraviolet radiation and powerful stellar winds blast outward, heating surrounding gas to millions of degrees until it's too energetic to collapse into new stars. It's a self-limiting cycle. The more stars form, the more they suppress further star formation by pushing gas away. In extreme cases, this feedback can even eject gas entirely, flinging it into intergalactic space like a cosmic pressure valve releasing steam. The galaxy's star-making days aren't just paused, they're put on hold until gravity can slowly pull that scattered gas back in, a process that might take billions of years. But stars aren't the only players in this balancing act. Supermassive black holes, awakened by the chaos of mergers, unleash their own form of feedback. As they devour gas, they spit out colossal jets of energy and radiation, carving bubbles in the surrounding material that act like against further star formation. These jets can stretch for hundreds of thousands of light years, their energy so immense that they heat entire galaxy clusters. In some systems, like the nearby galaxy M87, black hole feedback has effectively sterilized the core, leaving behind a gas-poor void where few new stars can form. This push and pull between creation and suppression is what keeps galaxies from becoming too massive too quickly. Without feedback, the largest galaxies would have exhausted their gas supplies eons ago, leaving the universe littered with stellar relics and little else. Instead, mergers trigger cycles of boom and bust, periods of furious star birth followed by long cosmic winters where galaxies rest and replenish. It's a rhythm as old as the universe itself, one that ensures galaxies evolve gradually rather than burning out in a blaze of glory. The evidence for this self-regulation is written across the cosmos. Take massive elliptical galaxies, the end products of countless mergers. Many are red and dead, packed with aging stars, but devoid of the gas needed to make new ones. Their feedback mechanisms work too well, shutting down star formation entirely. Meanwhile, younger galaxies like the Milky Way still have enough gas to spark occasional stellar births, their feedback systems operating in a gentler, more sustainable balance. What's truly remarkable is how finely tuned this process seems. Feedback doesn't just halt star formation, it sculpts it, ensuring galaxies grow at rates that match their environments. In dense galaxy clusters where mergers are frequent, feedback prevents galaxies from becoming bloated monsters. In quieter cosmic backwaters, it allows for slower, more measured growth. This universal regulatory system is why we see such diversity in galaxies today, from star-forming spirals to gas-poor ellipticals. And here's the profound takeaway. Feedback links the smallest scales to the largest. The death of a single massive star can influence the fate of an entire galaxy, just as a supermassive black hole's outburst can shape a cluster spanning millions of light years. It's a reminder that the universe operates through interconnected cycles, where destruction paves the way for new beginnings, and where even the most violent collisions leave behind a legacy of balance. Right now, the Andromeda galaxy appears as a faint smudge in our night sky, a distant neighbor floating 2.5 million light-years away. But make no mistake, it's hurtling toward us at nearly 250,000 miles per hour, pulled by gravity's unrelenting tug. In about 4 billion years, the Milky Way and Andromeda will meet in a slow-motion collision that will rewrite our cosmic neighborhood forever. This isn't science fiction. It's an inevitability written into the motion of the stars, a future so certain that astronomers can simulate it down to the last detail. At first, the changes will be subtle. As Andromeda looms closer, its faint glow will grow brighter, eventually rivaling the full moon. Then, the real show begins. Gravitational tides will warp both galaxies, stretching their spiral arms into long, shimmering streamers of stars. The orderly pinwheel of the Milky Way will distort, its familiar structure unraveling like a spinning top losing balance. Over millions of years, the two galaxies will swing past each other, then loop back, a cosmic dance that repeats until they finally merge into a single, colossal elliptical galaxy. Astronomers have already named it, a hybrid titan that will dominate our local universe. What does this mean for Earth? Remarkably, our planet might survive the chaos. The vast distances between stars mean our solar system will likely avoid catastrophic collisions, but the night sky will transform beyond recognition. The Milky Way's glowing band will vanish, replaced by a dazzling haze of stars from two merged galaxies. Andromeda's core, a brilliant golden orb, will dominate the heavens, its supermassive black hole now paired with our own in a binary embrace. New star clusters, forged in the merger's starbursts, will speckle the sky like diamonds scattered on black velvet. Yet the merger's aftermath holds even grander surprises. As settles, it may collide with the Triangulum Galaxy, our local group's third largest member, creating an even larger galactic behemoth. Over tens of billions of years, this unified galaxy will drift alone in an expanding universe, its neighbors into invisibility. Future civilizations, if any remain, will gaze up at a sky devoid of external galaxies, their history lost to cosmic expansion. This inevitable future reminds us that galaxies aren't static islands but dynamic creatures, growing and evolving through collisions. The Milky Way's fate is shared by countless others, each merger a step in the universe's relentless drive toward complexity. And while 4 billion years sounds impossibly distant, it's a blink in cosmic time, proof that even the grandest structures are fleeting, their stories written in starlight and gravity. While the titanic collisions between massive galaxies steal the cosmic spotlight, some of the most vital mergers happen on a far smaller scale, where dwarf galaxies, no bigger than 1,000th the Milky Way's size, plunge into their larger counterparts. These tiny cosmic wanderers might seem insignificant, but they're the unsung heroes of galactic evolution, delivering fresh supplies of gas and stars like interstellar grocery trucks. Without these modest mergers, giant galaxies would starve, their star-forming factories grinding to a halt as fuel reserves dwindled. Take the Large Cloud, a dwarf galaxy orbiting our Milky Way. Though just 1/100th its mass, this petite companion is a lifeline, dragging behind it a vast ribbon of hydrogen gas, the stream that's slowly raining down onto our galaxy. Every atom in that stream is potential star fuel, and similar deliveries happen across the universe. When a dwarf galaxy merges, its gas doesn't just blend in. It triggers waves of star formation, like throwing a match into dry tinder. The proof is etched across our own galaxy's halo, where ancient stellar streams, remnants of long-digested dwarfs, trace a history of silent feasts that kept the Milky Way vibrant. But hear what makes these small mergers special. They're gentle. Unlike the violent upheavals when giants collide, dwarf galaxies slip into larger ones with minimal disruption, their gas smoothly funneled into the galactic disk rather than blasted away by shockwaves. This makes them perfect cosmic delivery systems, small enough to avoid catastrophic damage, yet rich enough in pristine gas to reignite star formation. Some astronomers even believe dwarfs brought the Milky Way its youngest globular clusters, those dense balls of stars that orbit like celestial bees around a hive. The most surprising twist, dwarf galaxies might be responsible for the diversity of stars we see today. Their gas often carries different chemical fingerprints, lower in heavy elements compared to the well-mixed reservoirs of giant galaxies. When this unpolluted material merges, it dilutes the existing gas, allowing new generations of stars to form with unique compositions. It's like adding fresh ingredients to a simmering stew, subtly altering the flavor with each addition. Yet for all their contributions, dwarfs pay a steep price. Gravity shreds them during mergers, stretching their stars into faint, flowing ribbons that eventually dissolve entirely. The Sagittarius dwarf spheroidal, one of the Milky Way's current snacks, is already stretched into a stellar stream encircling our galaxy, a cosmic noodle wrapping around a fork. In a few billion years, nothing will remain but a slight overdensity of stars, a ghostly signature of its sacrifice. This quiet exchange, dwarfs feeding giants, is how galaxies avoid stagnation. Like rainfall replenishing a lake, these small mergers top up galactic gas reserves, ensuring star formation continues across cosmic time. And in a universe where the largest galaxies grew by consuming countless smaller ones, it's humbling to realize that even the tiniest players shape the grandest structures. Galaxies aren't meant to blaze with star-forming fury forever. Like aging giants stepping into retirement, many post-merger galaxies settle onto what astronomers call the red sequence, a cosmic graveyard of sorts where stellar birth has ceased, and only the long-lived red giants remain. This transformation isn't accidental. It's the inevitable consequence of a merger's violence, where the very forces that ignite starbursts also drain the galaxy of its lifeblood, gas. Picture a spiral galaxy rich with blue-white young stars, its arms shimmering with the glow of stellar nurseries. Now watch as a collision compresses its gas into a final, spectacular burst of star formation, a last hurrah before the lights go out. The most massive of these newborn stars burn bright and die young, their explosive deaths blasting away any remaining gas like a cosmic gust of wind extinguishing candles. What's left is a galaxy stripped bare, its fuel reserves spent, populated only by the older, cooler stars that glow with a reddish hue. These galaxies don't fade quietly. They're shoved onto the red sequence by the very mergers that once made them brilliant. The red sequence isn't just a curiosity, it's a dominant feature of the universe. In crowded galaxy clusters, up to 80% of galaxies belong to this red and dead population, their star-forming days long behind them. Many of these aging systems bear the subtle fingerprints of past mergers, faint shells of stars, disturbed orbits, or oddly shaped cores that betray a violent history. Take Messier 89, a seemingly smooth elliptical galaxy in the Virgo cluster. Its pristine appearance hides a turbulent past. Multiple mergers have robbed it of gas, leaving it a placid island of red giants where no new stars have formed for billions of years. Yet the journey to the red sequence isn't always immediate. Some galaxies experience a brief green valley phase, a transitional period where they're neither actively forming stars nor fully quenched. Here, they linger like cosmic zombies, not quite alive, not entirely dead, until feedback from supermassive black holes or residual merger effects finally snuff out the last traces of star formation. The process can take billions of years, a slow bleed of energy that leaves the galaxy colder, redder, and increasingly isolated from the vibrant star-forming galaxies around it. What's fascinating is how mergers determine a galaxy's final resting place. Head-on collisions between gas-rich spirals tend to trigger the most dramatic quenching, their starbursts consuming fuel so voraciously that nothing remains. Minor mergers, by contrast, might only partially quench a galaxy, leaving patches of star formation flickering like embers in a dying fire. Even the environment plays a role. Galaxies in dense clusters are more likely to join the red sequence early, as interactions with neighbors and hot cluster gas strip away their reserves. But the red sequence isn't the end of the story. These galaxies continue evolving, their stars gradually dimming as the universe expands around them. Over trillions of years, the red giants themselves will fade, leaving behind cooling white dwarfs and neutron stars, a silent, darkening relic of the merger that once reshaped them. It's a humbling thought. The same collisions that light up the cosmos with their brilliance also condemn galaxies to a slow, inexorable twilight. Yet without this cycle of creation and quenching, the universe would lack the diversity of galaxies we see today. From the vibrant spirals to the serene red ellipticals, each a snapshot of a different stage in the grand story of cosmic evolution. In the cosmic shadows, where dust clouds swirl thick enough to blot out starlight, some galactic mergers hide their brilliance behind veils of debris, only to glow with an intensity that defies imagination in the infrared spectrum. These are ultra-luminous infrared galaxies, or ULIRGs, cosmic powerhouses so shrouded in dust that their visible light is smothered, yet their heat signatures outshine entire galaxies. Imagine two spiral galaxies colliding, their gas and dust stirred into a frenzied whirlpool. As the merger compresses these particles, they become a thick, suffocating blanket, absorbing nearly all the visible light from the newborn stars within. But energy can't be contained. It escapes as infrared radiation, turning these galaxies into blazing beacons invisible to optical telescopes, but unmistakable to instruments like the James Space Telescope. The numbers behind ULIRGs are staggering. A typical ULIRG can emit up to 1 trillion times the luminosity of our sun, nearly all of it in infrared. That's more energy than 1,000 Milky Ways combined, packed into a region no larger than our solar system. Take 220, one of the most studied ULIRGs. Its core, obscured by dust, churns out new stars at a rate of hundreds per year, while twin supermassive black holes, each weighing hundreds of millions of solar masses, feast on the chaos. The dust doesn't just hide this frenzy, it supercharges it, trapping radiation until the particles themselves glow like embers in a cosmic forge. What makes these galaxies truly fascinating is their role as cosmic chameleons. To an optical telescope, they might appear as faint smudges or even go unnoticed entirely. But switch to infrared and they explode into view, their cores radiating with the heat of countless young stars and voracious black holes. This duality makes them critical to understanding how mergers reshape galaxies. Many astronomers believe ULIRGs are a fleeting phase, a galaxy's teenage years, where it's cloaked in the dust of its own explosive growth before stellar winds and black hole activity blow the shroud away, revealing a quasar or a mature elliptical galaxy. The of a ULIRG is a study in extremes. Initially, the dust is so thick that even X-rays struggle to escape. But as star formation peaks, the very stars that heat the dust also destroy it. Supernovae and stellar winds begin clearing the fog, while the growing black holes at the center unleash jets that carve pathways through the debris. Over millions of years, the galaxy transitions from an infrared monster to an optical powerhouse, its core finally visible as the dust dissipates. This metamorphosis suggests that many of the universe's quasars might have begun as ULIRGs, their brilliance initially veiled, then unleashed. Yet ULIRGs aren't just relics of the distant past. They're being discovered in our cosmic backyard, like the nearby galaxy NGC 6240, where a merger has ignited a firestorm of star formation visible only in infrared. Their prevalence in the early universe hints that they played a starring role in galactic evolution, perhaps serving as the primary factories for the heavy elements that make up planets and life. Today, they stand as a testament to the hidden forces sculpting the cosmos, reminding us that sometimes, the universe's most dazzling spectacles are the ones we can't see with our eyes, only feel with the warmth of their invisible light. Galaxy clusters are the universe's grand arenas, where collisions don't just happen, they're the main event. Picture a cosmic metropolis packed with hundreds, even thousands of galaxies, all orbiting a common center of gravity like bees swarming a hive. In these dense neighborhoods, mergers aren't rare spectacles. They're everyday occurrences, shaping galaxies into bizarre forms you'd never find in quieter corners of the cosmos. This is where the universe's most extreme transformations play out, where gravity's relentless pull turns orderly spirals into twisted wrecks and supermassive black holes into ravenous giants. Take the Coma Cluster, a bustling galactic city located 320 million light-years away. Here, galaxies zip past one another at dizzying speeds, their close encounters stripping away gas and stars like celestial bumper cars. Some galaxies, like the infamous Messier 87, emerge as dominant giants, having swallowed countless smaller neighbors to become the cluster's central behemoth. Others, like the whimsically named NGC 4921, sport long, shimmering tails of stars, tugged loose by the cluster's collective gravity. It's a galactic demolition derby where the survivors bear the scars of endless close calls. But the real drama unfolds in the cluster's heart, where galaxies don't just collide, they merge in rapid succession, piling gas onto already monstrous black holes. The result? Some of the most powerful active galactic nuclei in the universe, their jets carving through the cluster's hot gas like cosmic blowtorches. In the Perseus cluster, for instance, the central galaxy's black hole has erupted with such force that it's created vast bubbles in the surrounding gas, each spanning hundreds of thousands of light years. These eruptions aren't just destructive, They're regulatory, heating the cluster's gas and preventing it from cooling into new stars, a feedback loop that keeps the cosmic metropolis from overpopulation. What's fascinating is how these clusters act as time capsules, preserving snapshots of galactic evolution. In younger clusters like the still forming L cluster 9 billion light-years away, mergers are chaotic and frequent, birthing starburst galaxies shrouded in dust. Older clusters, by contrast, are quieter, their galaxies picked clean of gas by countless collisions, leaving behind red and dead ellipticals that glow faintly with the embers of ancient stars. The difference is stark. One is a cosmic nursery, the other a retirement home, yet both are products of the same relentless process. And here's the twist. Galaxy clusters aren't just passive backdrops for these collisions, they actively encourage them. The immense gravity of the cluster's dark matter halo acts like a traffic cop, herding galaxies into orbits where mergers are inevitable. Even galaxies that avoid direct hits are transformed by the cluster's harsh environment, their gas stripped away by the pressure of moving through the cluster's hot plasma, a process called ram pressure stripping. The result: a menagerie of oddities, from jellyfish galaxies, trailing star-forming tentacles to dark galaxies, lost nearly all their visible matter. Yet for all their violence, these clusters are also crucibles of creation. The same collisions that destroy galaxies also recycle their material, seeding future generations of stars and planets. The gas torn from one galaxy might fuel another's starburst, or feed a black hole whose energy will shape the cluster for eons. It's a reminder that in the universe's busiest neighborhoods, destruction and rebirth are two sides of the same coin, and that even in chaos, there's an underlying order, written in the language of gravity. The universe has a way of hiding its past, and one of its greatest disappearing acts involves the dwarf galaxies that should be swarming around giants like the Milky Way. Astrophysicists call this the missing satellite problem, a cosmic whodunit, where simulations predict hundreds of small companion galaxies orbiting large spirals, yet our telescopes spot only a fraction of that number. So where did they all go? The answer might lie in the relentless appetite of mergers, which have been quietly erasing these galactic crumbs from the cosmic record for billions of years. Imagine the early universe as a bustling neighborhood of dwarf galaxies, small, gas-rich systems that formed in the wake of the Big Bang. Gravity should have preserved many of them as satellites around larger galaxies, like fireflies trapped in a jar. But when we survey the Milky Way's vicinity, we find only about 60 confirmed dwarfs, a far cry from the thousands predicted by dark matter simulations. The discrepancy isn't a flaw in the science, it's a clue to a violent history. Mergers act like celestial sponges, absorbing these tiny galaxies so thoroughly that only the faintest traces remain. The dwarfs didn't vanish, they were digested. Evidence for this galactic vanishing act is etched into our own cosmic backyard. The Milky Way's halo is littered with stellar streams, elongated ribbons of stars that trace the orbits of long-dead dwarf galaxies. One of the most famous, the Enceladus stream, is the ghost of a dwarf galaxy torn apart 9 billion years ago, its stars now scattered across our skies like breadcrumbs from an ancient meal. Even the large and small clouds, our most prominent satellite galaxies, show signs of distortion from past encounters, their shapes stretched by the Milky Way's gravity. Given enough time, they too may dissolve into the halo, joining the ranks of the missing. But why don't all dwarfs meet this fate? The survivors, like the ultra-faint Draco and minor galaxies, cling to existence in orbits that keep them just beyond the Milky Way's grasp. Their dark matter halos, though puny compared to a giant spiral, act like protective shields, resisting tidal forces that would shred them apart. Others might have fallen into the galaxy long ago, but their gas was stripped away first, leaving them invisible to all but the most sensitive telescopes. The missing satellite problem isn't just about counting galaxies. It's about reading the faint signatures of a hidden war between gravity and survival. The implications stretch far beyond our local universe. If mergers are the primary culprit behind the missing dwarfs, then the galaxies we see today are just the survivors of a far richer cosmic ecosystem. Early epochs might have been teeming with thousands. Yet the mystery isn't fully solved. Some simulations suggest that the smallest dark matter halos, those that should host the tiniest dwarfs, may never have formed stars at all, leaving them invisible to our telescopes. Others propose that intense radiation from the early universe sterilized these halos, preventing gas from cooling and collapsing into stars. These dark galaxies would be ghosts in every sense, their presence detectable only through gravitational lensing or future advancements in dark matter detection. What's certain is that every large galaxy carries the scars of countless mergers, each one erasing smaller systems from the cosmic ledger. The missing satellite problem isn't just a puzzle. It's a testament to the dynamic, ever-changing nature of the universe, where even the smallest galaxies play a role in shaping the giants we see today. As telescopes grow more powerful, we may yet uncover more of these hidden threads, weaving together a fuller story of how galaxies grow, one vanished dwarf at a time. Look at any spiral galaxy, and you'll notice something peculiar at its core. A dense, glowing mound of stars rising from the center like a cosmic hill. These galactic bulges aren't just decorative features, they're scars from violent pasts, silent witnesses to collisions that reshaped entire galaxies billions of years ago. While the elegant arms of a spiral galaxy tell the story of orderly rotation, the bulge whispers secrets of chaos, its stars moving in erratic orbits that betray a history of gravitational turmoil. What creates these enigmatic structures? The answer lies in the frenzy of mergers. When galaxies collide, their stars don't just pass like ships in the night, they're flung into new paths by gravity's relentless pull. The outer disks stretch into sweeping arms, but the cores, they collapse inward, piling stars into a tight, chaotic swarm. Picture two crowds merging in a vast plaza. At the edges, people might drift apart, but at the center, the press of bodies becomes unbearable. That's how bulges form, stars crammed together by the gravitational equivalent of a cosmic traffic jam. Not all bulges are created equal, though. Some, like the Milky Way, are pseudo-bulges flattened and disk-like, their stars still rotating in an orderly fashion, hinting at a quieter formation through slow gas accumulation. But the classical bulges are different. These are the true products of mergers, their stars jostling in random orbits like bees in a hive, their chemistry revealing a violent origin. Take the Andromeda galaxy's bulge. Its stars are older and richer in heavy elements than its disk, a fingerprint of ancient collisions that forged its core long before its spiral arms took shape. The most telling clue to a bulge's violent birth lies in its star's motions. While disk stars orbit serenely around the galactic center, bulge stars plunge in every direction, up, down, sideways, a hallmark of gravitational chaos. It's as if the galaxy's core remembers the trauma of its youth, its stars forever restless from the encounter that birthed them. Even the black holes at the centers of these bulges bear witness. The more massive the bulge, the more massive the black hole, a cosmic ledger tracking how much violence the galaxy has endured. Yet bulges aren't just relics, they're active players in galactic evolution. Their immense gravity anchors the spiral arms, stabilizing the galaxy against further disruptions. They're also cosmic crucibles, where dense gas clouds ignite furious star formation, and where supernovae seed the galaxy with heavy elements. Without bulges, spirals might unravel entirely, their delicate structures torn apart by passing galaxies or internal instabilities. What's truly humbling is realizing that our own Milky Way's bulge, a faint peanut-shaped glow in Sagittarius, holds clues to a cataclysm that predates the Earth. Some of its stars may have formed in a smaller galaxy that merged with the infant Milky Way, their orbits scrambled beyond recognition. Others might be survivors of the Gaia-Enceladus collision, a dwarf galaxy swallowed 9 billion years ago. Every bulge is a mosaic of stolen stars, a monument to the mergers that built the cosmos, one violent embrace at a time. When galaxies collide, the stars within them aren't just spectators, they're soldiers in a gravitational war, and not all will make it out alive. For every dazzling starburst or elegant tidal tail formed in a merger, there's a butcher's bill to pay, a toll exacted by the universe's relentless physics. Some stars are ripped from their galactic homes entirely, catapulted into the abyss between galaxies where they'll drift, cold and alone, for eternity. Others meet far more violent ends, crushed in the gears of supermassive black holes or obliterated in supernova explosions that outshine entire solar systems. Take the rogue stars first, lonely exiles flung into intergalactic space at speeds so high they escape their galaxy's gravity forever. These aren't rare anomalies. Astronomers estimate billions wander the voids between galaxies, their faint light detectable only because they outnumber the darkness. Some are hurled away by the gravitational slingshot of a passing black hole, others by the chaotic tides of merging galaxies. Imagine our own sun, suddenly ejected from the Milky Way, its planets frozen in an instant, their orbits now carrying them through an endless night where the nearest star is impossibly distant. That's the fate of these stellar castaways, doomed to fade into the cold as their nuclear furnaces sputter out over trillions of years. But ejection is a mercy compared to other fates. In the crowded core of a merging galaxy, stars can be torn apart entirely, not by collisions, which are vanishingly rare, but by the gravitational extremes near supermassive black holes. When a star ventures too close, tidal forces stretch it into a spaghetti-like strand of plasma in an event poetically named. The star's material then spirals into the black hole, heating to millions of degrees and glowing briefly brighter than a supernova before vanishing. These tidal disruption events are the universe's way of erasing stars from existence, leaving behind only a flicker of X-rays as a tombstone. Then there are the stars that go out in a blaze of glory. In the starburst regions of merging galaxies, massive stars burn through their fuel in just a few million years, ending their lives in titanic supernovae. These explosions aren't just spectacular, they're transformative, scattering heavy elements like iron and gold into the surrounding gas, where they'll someday form new stars, planets, and perhaps even life. But for every supernova that enriches the cosmos, countless smaller stars are caught in the crossfire. Their atmospheres stripped by shockwaves, their orbits destabilized, they become collateral damage in the galaxy's rebirth. The irony, some stars survive the merger only to be swallowed by the very black holes their deaths helped grow. As supermassive black holes at the centers of galaxies feast on gas and stars, they grow more massive, their gravitational reach expanding. Stars that might have orbited safely for billions of years are suddenly on the menu, pulled inexorably toward an event horizon from which not even light can escape. It's a cosmic, the merger creates the conditions for the black hole to grow, and the black hole, in turn, consumes the stars the merger spared. Yet even in this stellar carnage, there's a strange beauty. The rogue stars drifting through the void may one day be captured by another galaxy, their light joining a new stellar chorus. The atoms forged in supernovae will seed future generations of stars and planets. And the black holes, their growth regulates the galaxies they inhabit, preventing runaway star formation that could burn through a galaxy's gas too quickly. The butcher's bill of galactic mergers is steep, but it's also the price of cosmic evolution. a reminder that destruction and creation are forever entwined in the universe's grand narrative. Its famous classification system, the cosmic filing cabinet where galaxies are neatly sorted into spirals, ellipticals, and irregulars, works beautifully for a calm, unchanging universe. But throw galactic mergers into the mix, and that orderly system starts to unravel. Like trying to categorize a burning house as residential or industrial, this framework struggles to capture the chaos of colliding galaxies, where familiar shapes dissolve into something entirely new. Take the classic spiral galaxy, a pristine pinwheel of stars with sweeping arms and a glowing core. In system, it sits comfortably on one branch of his tuning fork diagram, but let that spiral merge with another and the transformation begins. Tidal forces stretch its arms into long, shimmering streams, its delicate disk thickens and warps, star-forming regions ignite like flashbulbs across its body. Within a few 100 million years, that elegant spiral might resemble nothing in its original scheme. It's not quite a spiral anymore, not yet an elliptical. It's something in between, a cosmic chimera defying classification. This is where the sequence hits its limits. Designed in the 1920s, it assumed galaxies evolved in isolation, their shapes dictated by initial conditions rather than violent encounters. But modern astronomy reveals a universe far more dynamic, where mergers act like cosmic blenders, remixing galaxy types with abandon. The result, a growing zoo of hybrid systems that blurs clean lines. Some, like polar ring galaxies, feature a central elliptical surrounded by a perpendicular ring of gas and stars, the aftermath of a smaller galaxy being torn apart and its debris caught in a bizarre orbit. Others, like shell galaxies, show concentric ripples of stars, the ghostly echo of a spiral shredded and layered like an onion. Even elliptical galaxies, once thought to be the boring end products of mergers, are now revealing hidden complexity. Imagine them as smooth, featureless spheres of old stars, but advanced telescopes show many are laced with faint structures. Tidal tails, dust lanes, even disrupted spiral arms lurking beneath their placid surfaces. These ellipticals hint that not all mergers erase a galaxy's past entirely. Some preserve whispers of their pre-collision identity, like a song played backward in the static. The most telling challenge to system comes from the universe's youngest galaxies. In the early cosmos, mergers were constant, and few galaxies fit neatly into spiral or elliptical categories. Instead, they're often classified as clump clusters, lumpy, irregular masses where star-forming regions blaze like cities seen from space, their light tangled in knots of dust and gas. These primordial systems suggest that the sequence might be less a universal rulebook and more a snapshot of galaxies at a relatively quiet stage in cosmic history. Yet for all its shortcomings, system isn't obsolete, it's evolving. Astronomers now use it as a starting point, layering on new classifications to account for merger-driven oddities. Terms like post-starburst, ultra-diffuse, or blue nugget galaxies have joined the lexicon, each describing phases where collisions have temporarily a galaxy's original identity. It's a reminder that classification isn't about putting the universe in boxes, but about listening to the stories galaxies tell, especially when those stories are written in the scars of collisions. The next time you see tuning fork diagram, remember, it's not wrong, just incomplete. Like a map missing half its landmarks, it guides us through a calmer corner of the cosmos while the real action happens off the edges, where galaxies crash, merge, and rewrite their own definitions. And in those chaotic encounters, we're witnessing the universe's true creativity, not just arranging galaxies, but reinventing them. When galaxies collide, the resulting starbursts don't just light up the cosmos, they arm it with celestial demolition crews. Supernovae, the universe's most violent explosions, erupt in waves during mergers, their shockwaves rippling through galaxies like cosmic grenades. These aren't just spectacular fireworks, they're transformative events, sculpting galaxies by blasting away the very gas that fuels star formation. Imagine a wildfire so intense it burns away the forest floor, leaving the soil barren. Supernovae do the same to galaxies, their fury clearing space for future evolution while scattering the seeds of new worlds. The numbers are staggering. In a single starburst galaxy like Messier 82, triggered by a nearby encounter, supernovae explode at 10 times the Milky Way's rate, one every few decades. Each detonation unleashes as much energy as a star emits in its entire lifetime, compressed into weeks of brilliance. The shockwaves race outward at thousands of miles per second, heating surrounding gas to millions of degrees until it's too energetic to collapse into new stars. This feedback loop is nature's way of preventing galactic burnout. Supernovae sacrifice short-term star formation to ensure galaxies don't exhaust their fuel reserves too quickly. But destruction here is just the first act. These explosions are also cosmic alchemists, forging elements far heavier than hydrogen and helium in their cores. When a massive star goes supernova, it fuses atoms into iron, gold, and uranium, then hurls them into space like a gardener scattering seeds. The Orion Nebula, a nearby stellar nursery, is laced with these metals, proof of ancient supernovae that enriched its gas. Without mergers to concentrate star formation, these elements might remain locked in small pockets, never spreading widely enough to form rocky planets like Earth. The aftermath of these explosions reveals their dual role. In galaxies like NGC 4049, astronomers have spotted gigantic cavities carved by successive supernovae, their walls glowing with expelled heavy elements. These structures act like cosmic conveyor belts, transporting enriched material far from its birthplace. Some gas escapes entirely, venting into intergalactic space where it might one day fuel distant galaxies. Other material lingers, eventually cooling into dusty tendrils that wrap around the galaxy like a shroud, waiting for gravity to recycle it into future stars. What's truly remarkable is how these events scale across time. In the early universe, dwarf galaxies, small and fragile, were particularly vulnerable to supernova feedback. A single energetic explosion could eject most of a dwarf's gas, stunting its growth forever. This might explain why so many tiny galaxies today are quenched, their star formation snuffed out eons ago. By contrast, massive galaxies like the Milky Way withstand these blasts, their deeper gravitational wells trapping enough gas to keep forming stars, albeit in bursts paced by mergers. Yet supernovae aren't just forces of change, they're also storytellers. The composition of stars born after a merger bears the fingerprints of these explosions, their atmospheres rich in elements forged in death. Our own sun, a later generation star, carries traces of supernova debris from mergers that shook the Milky Way long before its birth. Every iron atom in our blood, every calcium particle in our bones, was likely born in the heart of a dying star during some ancient galactic collision. So when we witness a merger's starbursts lighting up the cosmos, we're not just watching stars being born, we're seeing the factories that will forge the building blocks of future worlds. The explosions may seem destructive, but they're the universe's way of redistributing wealth, ensuring that no galaxy and no planet is left without the ingredients for complexity. In the grand cycle of galactic evolution, supernovae are both end and beginning, demolition crews and architects, erasing one chapter while scribbling the first lines of the next. Galaxies may seem eternal, but they carry hidden scars, fingerprints of ancient collisions etched into their stars, their shapes, even their chemistry. Like detectives piecing together a crime scene from scattered clues, astronomers scan the skies for these cosmic fossils, reconstructing mergers that unfolded when Earth was still a molten rock. The evidence is everywhere if you know where to look. Take the Andromeda galaxy's giant stellar halo, a vast, diffuse cloud of stars surrounding its familiar spiral disk. These stars aren't just randomly scattered. They form intricate ripples and streams, the shredded remains of smaller galaxies devoured over billions of years. It's a galactic archaeology site where every star cluster holds a chapter of the past. Then there are the stars themselves, celestial time capsules with chemical stories to tell. Stars born in different galaxies carry distinct elemental signatures, like accents betraying their origins. When galaxies merge, their stellar populations mix, but the chemistry remains. The Milky Way's halo contains stars with unusually low metal content, a telltale sign they were forged in small, ancient galaxies that lacked the resources to enrich their gas with heavier elements. These stellar immigrants bear silent witness to our galaxy's violent youth, when it grew by cannibalizing its neighbors. But perhaps the most haunting fossils are the ones we can't see directly, dark matter halos. These invisible cocoons envelop every galaxy, and when mergers occur, their dark matter intermingles in ways that distort the visible galaxy's shape. Some galaxies, like the shell galaxy NGC 3923, exhibit concentric rings of stars, ghostly echoes of a smaller spiral galaxy punched straight through its center, like a stone dropped in water. The ripples from that impact remain frozen in starlight, a snapshot of violence preserved for eons. Even a galaxy's motion can reveal its past. Stars orbiting against a galaxy's rotation, so-called counter-rotating stars, are almost always prisoners of war, captured from a galaxy that merged on a retrograde trajectory. The Milky Way's Omega cluster, a dense ball of millions of stars, moves in such an odd orbit that astronomers suspect it's the surviving core of a dwarf galaxy torn apart long ago. These rebellious stellar swarms are living fossils, their defiance against galactic norms a testament to the chaos that birthed them. The most astonishing part, these fossils aren't just historical curiosities, they're reshaping our understanding of galaxy evolution. By studying them, we've learned that galaxies like the Milky Way didn't grow slowly and steadily, but in sudden bursts triggered by violent mergers. Every distorted shape, every oddball star cluster, every chemical anomaly is a brushstroke in a larger cosmic self-portrait, one that reveals galaxies not as isolated islands, but as products of an endless gravitational dance, where destruction and rebirth are forever entwined. Galactic archaeology isn't about digging through cosmic dirt, it's about decoding the universe's history written in starlight. Every merger leaves behind clues, like pages torn from a celestial history book, and with tools like the James Space Telescope, we're finally learning to read them. Imagine tracing the Milky Way's ancestry not through fossils, but by studying the motions, compositions, and even the oddball orbits of stars that shouldn't be here. These stellar immigrants are the smoking guns of ancient collisions, their paths and chemistries betraying origins in long-vanished galaxies. Take the Gaia spacecraft's revelations. By mapping the Milky Way's stars with unprecedented precision, it uncovered ghostly streams weaving through our galaxy's halo, the shredded remains of dwarf galaxies swallowed billions of years ago. One of the most dramatic, the Gaia-Enceladus stream, tells of a collision so violent it may have reshaped the Milky Way's entire structure in its youth. But these are just the obvious scars. Fainter trails, detectable only with next-generation telescopes, promise to reveal mergers so ancient their participants have dissolved entirely, leaving only subtle ripples in the distribution of stars. This is where the James Space Telescope becomes a time machine. Its infrared eyes can pierce through dust to spot the faintest, most distant stellar streams, relics of mergers from the universe's first few billion years. By studying these structures in galaxies millions of light-years away, we're compiling a cosmic family album, seeing how giants like Andromeda or the Milky Way grew through countless smaller unions. Even more tantalizing are the chemical fingerprints can detect. Stars born in different environments carry distinct ratios of elements, like oxygen to iron acting as cosmic barcodes that reveal their birthplace. Find a cluster of stars with matching barcodes but wild orbits, and you've likely uncovered the survivors of a galactic wreck. The future goes beyond mere detection. Projects like the Sea Observatory will scan the entire visible sky every few nights, catching mergers in action across cosmic time. Combine that with gravitational wave detectors like LISA, which will sense the ripples from colliding black holes, and we're building a multi-messenger picture of galactic evolution. It's like assembling a jigsaw puzzle where some pieces come from starlight, others from space-time vibrations, and others still from the invisible tug of dark matter. What's at stake isn't just a backward glance, it's a forecast. By understanding how mergers shaped galaxies in the past, we can predict the Milky Way's fate when it collides with Andromeda. Will the merger trigger a quasar, sterilizing our galaxy's core? Will Earth's night sky someday glow with the light of 100 billion new stars? Galactic archaeology doesn't just dig up the past, it hands us the keys to the future. And with every new telescope, every deeper observation, we're not just reading the universe's history, we're learning how it writes itself. Galactic mergers aren't all cut from the same cosmic cloth. Some are drenched in gas, bursting with newborn stars, while others unfold like ghostly dances between barren, aging giants. Astronomers call this the divide between wet and dry mergers, a fundamental split that dictates whether a collision will ignite a fireworks show of star formation or leave behind a quiet, featureless relic. The difference boils down to one critical ingredient: gas. In wet mergers, galaxies arrive flush with interstellar fuel, their reservoirs of hydrogen and helium primed to ignite under the pressure of collision. Picture two clouds of gas and stars slamming together, their material compressing into dense knots where gravity takes over, sparking starbursts so intense they can outshine entire galaxies. The antennae galaxies epitomize this. Their tangled arms glitter with young blue star clusters, each one a testament to the transformative power of gas-rich collisions. Dry mergers, by contrast, are the cosmic equivalent of blending two bowls of dust. These gas-poor galaxies, often aging ellipticals or spirals that long ago exhausted their star-forming fuel, collide without the dramatic bursts of new stellar life. Instead of fiery nurseries, their mergers produce smooth, puffier ellipticals where stars orbit in every direction, like bees in a swollen hive. The galaxy NGC 4125 offers a pristine example, a massive elliptical thought to be the product of multiple dry mergers, its golden glow composed entirely of ancient stars with no trace of the blue sparkle seen in younger systems. Without gas to reignite star formation, these galaxies become celestial retirement homes, their stellar populations quietly fading over eons. What's fascinating is how this dichotomy shapes the universe's diversity. Wet mergers dominate the cosmic frontier, where galaxies are still gas-rich and vibrant. They're the engines behind infrared galaxies and quasars, their furious star formation shrouded in dust but radiating unimaginable heat. Dry mergers, meanwhile, rule dense galaxy clusters, where frequent encounters and hot intergalactic plasma have long since stripped galaxies of their gas. Here, collisions are silent affairs, adding mass without light, turning galaxies into ever larger but dimmer giants. The Milky Way's future collision with Andromeda will likely start wet. Both galaxies still have some gas, but end dry, their merged form eventually settling into a gas-poor elliptical as stellar winds and black hole feedback blow away the remaining fuel. Yet even this binary has its exceptions. Some mergers are damp, a middle ground where modest gas reserves trigger limited starbursts, leaving galaxies neither fully reborn nor entirely stagnant. Others, like the mixed mergers between a gas-rich spiral and a gas-poor elliptical, create hybrid systems where new stars form in patches amid an otherwise quiescent backdrop. These nuances remind us that galactic evolution isn't a checkbox but a spectrum, with each collision writing its own unique story in the interplay of gravity, gas, and time. The wet-dry divide also hints at a deeper cosmic rhythm. Early in the universe's history, wet mergers dominated, building galaxies from pristine gas and filling the cosmos with starlight. Today, as galaxies age and clusters grow denser, dry mergers take center stage, their quieter unions marking the universe's gradual shift from creation to endurance. It's a reminder that galaxies, like stars, have, and the difference between a fiery youth and a serene old age often comes down to something as simple as the presence or absence of gas, the universe's most transformative ingredient. Peering into the heart of a galactic collision in real time is impossible. These cosmic ballets unfold over hundreds of millions of years. But what if we could speed up the universe? Enter the realm of supercomputers, where astrophysicists recreate mergers down to the last stellar detail, compressing eons into days. These aren't just fancy animations. They're precision instruments, virtual laboratories where scientists test theories by crashing galaxies together again and again, tweaking variables like cosmic chefs perfecting a recipe. The results: stunningly accurate models that decode mysteries no telescope could solve alone. Take dark matter, the invisible glue holding galaxies together. Since it emits no light, its behavior during mergers remains hidden from direct observation. But simulations reveal its ghostly fingerprints. When researchers at the University of Zurich modeled the bullet cluster collision, their supercomputer showed dark matter halos sliding through each other like phantom ships, exactly matching the real cluster's gravitational lensing patterns. Without simulations, we'd have no way to confirm that dark matter, unlike gas, barely interacts, passing through itself in regular matter like a shadow through a wall. Black hole dynamics are another puzzle cracked by virtual collisions. When galaxies merge, their central supermassive black holes begin a gravitational tango, spiraling toward a cataclysmic union. Telescopes spot the aftermath, quasars or recoiling black holes, but the process itself is too slow to witness. Simulations like those run on NASA's Pleiades supercomputer show something extraordinary. Black holes often stall just a few light years apart, trapped in a cosmic standoff that can last billions of years. Only when a third black hole or a massive gas cloud intervenes do they finally merge, unleashing gravitational waves. This final parsec problem explains why some galaxies, like NGC 6240, host dual black holes instead of single behemoths. The real power of simulations lies in their predictive edge. Before the Space Telescope captured the antennae galaxies, tangled arms, supercomputers had already recreated their star-forming arcs down to the. When the James Telescope spotted young globular clusters in merging galaxies last year, it confirmed what models had hinted at for decades, that these dense stellar cities form preferentially in collision zones. And when LIGO detected gravitational waves from black hole mergers, the ripple patterns matched supercomputer predictions with eerie precision, validating theories under extreme conditions. Yet these virtual universes aren't perfect. Simulating every star in a galaxy is impossible. Even the fastest supercomputers must use shortcuts, treating stars as statistical populations rather than individual points. Gas physics introduces another layer of complexity, requiring algorithms to mimic turbulence, magnetic fields, and radiation pressure across light years of virtual space. The Frontier supercomputer at Oak Ridge National Lab, currently the world's fastest, dedicates millions of processor hours to a single merger simulation. Its calculations so intricate they generate petabytes of data. What's next? Next-generation simulations aim to bridge scales, modeling not just galaxies but the planets within them. Imagine tracking Earth's orbit during the Milky Way Andromeda collision, or predicting which star systems might be flung into the void. Others incorporate quantum-level physics to probe the first seconds after black holes merge, where spacetime itself becomes a turbulent sea. As telescopes like the observatory prepare to map billions of galaxies, simulations will be the stone translating raw data into cosmic history, one virtual collision at a time. Among the countless galaxies captured by telescopes, hidden in their spirals and collisions, lies a treasure trove of data too vast for any single researcher, or even any supercomputer to fully process. That's where you come in. Projects like Galaxy Zoo have turned the hunt for merging galaxies into a global team effort, inviting everyday people to become cosmic detectives. With just a laptop and curiosity, volunteers have uncovered rare merger stages, spotted oddities algorithms missed, and even discovered entirely new galactic phenomena. It turns out the human brain's knack for pattern recognition, the same skill that lets us pick out faces in clouds or constellations in stars, makes us uniquely suited to sift through the universe's chaos. Take the case of a mysterious green blob of gas glowing near spiral galaxy IC 2497. When Dutch schoolteacher Van stumbled across it while classifying galaxies for Galaxy Zoo, astronomers were baffled. The object, later revealed to be a light echo from a quasar outburst, had been hiding in plain sight, overlooked by professionals and software alike. This wasn't a fluke. Volunteers have since identified thousands of merging galaxies in delicate stages, like the taffy galaxies, their stretched arms locked in a gravitational pull, or vorticist galaxies, their shapes twisted like abstract paintings. These discoveries aren't just pretty pictures, they're critical data points for understanding how collisions unfold across cosmic time. What makes human classifiers so indispensable? Machines excel at measuring galaxy shapes or calculating light curves, but they falter when faced with the messy, asymmetrical reality of mergers. A computer might dismiss a distorted spiral as noise, while a human eye catches the subtle signs of an ongoing collision. The off-center nuclei, the faint tidal tails, the warped disks that betray gravitational turmoil. It's the cosmic equivalent of spotting a face in a crowd, intuition honed by evolution. Galaxy Zoo leverages this by presenting users with real telescope images, asking simple questions about a galaxy's shape or odd features. Each classification is cross-checked by multiple volunteers, creating a crowdsourced map of galactic interactions more nuanced than any algorithm could produce. The impact goes beyond cataloging. In 2014, Galaxy Zoo volunteers helped identify a population of red spiral galaxies, anomalies that shouldn't exist according to old models. These systems, rich in old stars yet stubbornly retaining their spiral arms, forced astronomers to rethink how mergers preserve or destroy galactic structure. Similarly, citizen scientists flagged galaxies with overlapping but non-interacting disks, proving that not every close encounter leads to a merger. These distinctions are vital for simulations. Without accurate real-world examples, models risk veering into theoretical fantasy. But Galaxy Zoo is just the beginning. Spin-off projects like Radio Galaxy Zoo enlist the public to trace jets from supermassive black holes across radio and infrared images, while Zoo dives into deep-field observations. Some volunteers have co-authored scientific papers, Others, like the retired teacher who discovered a galaxy cluster now nicknamed Treasure Chest, have left their mark on astronomy textbooks. The project's genius lies in its simplicity. No D required, just a willingness to look closely and wonder. In an era where AI dominates headlines, Galaxy Zoo reminds us that some puzzles still need human intuition. Those faint smudges on your screen might be galaxies in the act of merging, their light traveling billions of years to reach your eyes. And with every click, you're not just observing the universe, you're helping to decode its grandest collisions, one galaxy at a time. While galactic collisions dominate the narrative of cosmic evolution, some galaxies defy the odds entirely, floating alone in the vast, empty stretches between galaxy clusters like lone travelers in a desert. These isolated galaxies, untouched by mergers for billions of years, are the universe's control group, offering a rare glimpse into what galaxies look like when left to evolve in solitude. Without the gravitational tug-of-war of collisions, their stories unfold differently, their shapes and star-forming habits preserving a quieter, more undisturbed version of cosmic history. Take NGC 6503, a spiral galaxy adrift in the local void, a region of space so empty it's been called a cosmic desert. Unlike the Milky Way, which bears the scars of past mergers in its halo of stellar streams, NGC 6503's structure is pristine, its spiral arms symmetrical, its disk undisturbed by tidal forces. Star formation here follows a gentle rhythm, untriggered by the violent gas compression of collisions. It's a galaxy frozen in time, its evolution dictated not by chaos, but by the slow, steady consumption of its own gas reserves. The rarity of these isolates makes them invaluable. By comparing them to merger-heavy galaxies, astronomers can tease apart which features, like bulges, bars, or star-forming rings, arise from internal processes versus external violence. For instance, many isolated spirals lack the thick central bulges common in galaxies like Andromeda, suggesting that bulges often form or amplify during collisions. Others, like UGC 4879, exhibit unusually low metallicity in their stars, hinting that mergers might be crucial for dispersing heavy elements across galaxies. Without the mixing caused by collisions, these galaxies remain chemically undiluted, their stars telling a but less enriched story. Yet isolation isn't always peaceful. Cut off from the fresh gas infall that mergers provide, some lone galaxies slowly starve, their star formation sputtering out as they exhaust their fuel. They become quiet spirals, their disks fading into redness as their stellar populations age without renewal. Others paradoxically blaze with unexpected star formation, their gas reservoirs so untouched that they've avoided the quenching effects of black hole feedback or supernova winds. These outliers challenge assumptions, proving that galaxies don't need collisions to thrive, just as they don't always need solitude to wither. The most profound lesson from these cosmic hermits: mergers aren't destiny. While they dominate galactic evolution, they're not the sole authors of a galaxy's story. In the voids far from the gravitational fray, galaxies carve their own paths, proof that the universe has room for both the chaotic and the serene, the collided and the alone. Their existence is a reminder that for every titanic clash shaping the cosmos, there's also silence, undisturbed and enduring, writing its own quiet chapter in the dark. The universe keeps its own timeline, and the pages of this cosmic history book are written in the twisted shapes of galaxies. Astronomers have long searched for ways to date these violent encounters, and their solution is as ingenious as it is simple. They've built a merger clock by counting the number of distorted galaxies at different epochs. The more warped spirals and tidal tails they spot in a given slice of cosmic time, the more frequent collisions must have been during that era. And what this clock reveals is startling. The universe's past was a far more chaotic place than we see today, with mergers reaching a fever pitch around 10 billion years ago, when galaxies were crammed closer together and gravity had more opportunities to pull them into violent embraces. Zoom into that ancient era, and the sky would have been a spectacle of galactic carnage. Young, gas-rich spirals, smaller and more fragile than today's giants, slammed together in dizzying numbers, their collisions igniting fireworks of star formation visible across the cosmos. Telescopes like in JWST have captured snapshots of this frenzy in deep-field images, where distant galaxies appear oddly shaped, stretched, or paired in tight gravitational dances. These aren't just random oddities. They're time-stamped evidence of an epoch when mergers were the universe's primary construction crew, building today's massive galaxies from smaller, chaotic pieces. But the merger clock doesn't tick uniformly. As the universe expanded, galaxies grew farther apart and the frequency of collisions slowed. By comparing nearby galaxy clusters, where mergers still occur to their ancient counterparts, astronomers can trace this decline. The Antennae galaxies, a nearby merging pair, offer a glimpse of what was once commonplace. 10 billion years ago, such sights were 10 times more frequent, with galaxies colliding in a relentless cycle of creation and destruction. Today, mergers are rarer, but their legacy lives on in the elliptical galaxies and stellar halos they left behind. The real magic of the merger clock lies in its details. By cataloging different stages of collisions, from initial close approaches to final mergers, astronomers can reconstruct timelines for individual galaxies. The Milky Way, for instance, bears chemical and kinematic fingerprints of a major merger 9 billion years ago, when a dwarf galaxy named Enceladus was torn apart and absorbed. Similar forensic techniques applied to Andromeda reveal its own violent past, with stellar streams hinting at least 2 significant mergers. These aren't just historical curiosities. They're clues to how galaxies like ours grew from the chaos of the early universe into the ordered spirals we recognize today. Yet the merger clock also holds mysteries. Why did collisions peak when they did? Was it the universe's density at that time, or did dark matter play a role? And what about the outliers, galaxies that somehow avoided mergers entirely, floating undisturbed for billions of years? Each question adds nuance to the story, reminding us that while the merger clock ticks for the cosmos as a whole, individual galaxies dance to their own rhythms. One thing is certain, this clock is still ticking. The Milky Way and Andromeda's future collision is just one more tick in a grand cosmic countdown, a reminder that even in today's quieter universe, the forces that shaped galaxies billions of years ago are still at work, slowly, inevitably, rewriting the night sky one collision at a time. When galaxies collide, they don't just rearrange stars. They become cosmic polluters on an unimaginable scale, spewing enriched gas into the vast emptiness between galaxies. This intergalactic pollution might sound destructive, but it's actually one of the universe's most vital recycling programs. Picture a galactic collision as a high-pressure factory. As merging galaxies compress gas clouds, they trigger supernovae that blast heavy elements like oxygen, carbon, and iron far beyond the galaxy's gravitational grasp. These metals don't vanish into the void. They become the raw materials for future cosmic structures, drifting through the intergalactic medium until gravity pulls them into new stellar nurseries billions of years later. The numbers behind this pollution are staggering. A single merging galaxy pair can eject millions of suns worth of gas, laced with enough heavy elements to forge countless rocky planets. The famous Mice galaxy's 2 spirals entwined in a gravitational dance are currently expelling a trail of enriched gas stretching over 300,000 light-years. Similar outflows have been spotted in infrared galaxies, where starburst-driven winds carry metals at speeds exceeding 2 million miles per hour. These aren't gentle leaks, but of material, powered by the combined energy of supernovae and supermassive black holes feasting on merger debris. What's astonishing is how far this pollution travels. Simulations show that merger-ejected metals can drift for hundreds of millions of light years, mixing with primordial hydrogen in the cosmic web. The proof: even the most distant, ancient gas clouds contain trace metals, evidence that mergers have been enriching the cosmos since the first galaxies formed. The stream, a river of gas trailing our Milky Way, bears the chemical fingerprints of past collisions, its slightly elevated iron content betraying origins in some long-ago galactic upheaval. This intergalactic pollution does more than drift, it transforms the universe's architecture. When enriched gas cools and falls into galaxy clusters, it forms the spectacular cooling flows that fuel central elliptical galaxies. The Virgo cluster's M87, for instance, owes its monstrous size partly to recycled metals from countless mergers, which helped its gas cool efficiently and form generations of stars. Conversely, in the early universe, metal pollution may have prevented dwarf galaxies from forming, as enriched gas radiates heat more effectively, resisting gravitational collapse. The ultimate irony is that this pollution enables life. Every iron atom in your blood, every calcium particle in your bones, likely spent eons drifting between galaxies after being forged in some ancient merger starbursts. Our solar system condensed from gas that had been polluted multiple times over, a testament to how the universe's most violent events seed the ingredients for complexity. Far from being mere destruction, these intergalactic ejections are the universe's way of spreading its riches, ensuring no corner of the cosmos remains forever pristine. Human brains evolved to navigate a world of apples falling from trees and predators chasing prey, not galaxies colliding over billions of years. Our intuition fails spectacularly when confronted with the reality of cosmic mergers, where time stretches beyond civilizations and distances dwarf every human journey. Consider this: when Andromeda finally meets the Milky Way, the first close pass will take longer than all of recorded human history. Stars won't crash, they'll glide past like ships in an endless ocean, their paths bending so gradually you'd need a spanning to notice. This disconnect explains why even the most detailed simulations feel surreal. Artists render mergers as explosive fireworks, but reality is subtler. A ballet where gravity's pull is weaker than a spider's silk thread, yet unstoppable over epochs. A galaxy's spiral arm doesn't tear like paper. It stretches like taffy over hundreds of millions of years, its stars adjusting orbits with imperceptible patience. The violence isn't in sudden impacts, but in relentless inevitability, as unstoppable as continental drift, yet far grander. Our struggle to grasp these scales reveals a deeper truth. The universe operates beyond human narrative structures. We crave beginnings and endings, but mergers have neither, just transitions. A galaxy doesn't die when consumed. Its stars join new constellations, its gas fuels fresh stellar births. Even terms like collision mislead. Galaxies merge like two crowds mingling, not cars crumpling. Scientists combat this by translating cosmic timelines into relatable metaphors. If the Milky Ways were a feature film, a merger would unfold in a single frame. Yet no analogy fully bridges the gap between human perception and cosmic reality. Perhaps the greatest irony is that we're trying to comprehend these events using minds shaped by the very mergers we study. The atoms in our brains, the carbon, oxygen, and iron, were forged in stars born from galactic collisions long ago. We're stardust attempting to understand its own origins, peering through telescopes at processes too vast to hold in thought, yet intimate as our own existence. The limits of our imagination aren't failures, they're invitations to keep exploring, to let the universe stretch our minds as it stretches time itself. Galaxies collide, stars scatter, and black holes merge in a cosmic ballet spanning billions of years. Yet the most profound impact of these events might not be on the universe itself, but on how we see our place within it. Every time astronomers capture two galaxies entwined in a gravitational embrace, we're confronted with an unsettling truth. The cosmos is not some static backdrop to human existence, but a seething, ever-changing arena where even the grandest structures are fleeting. The Milky Way, our island home with its hundreds of billions of stars, isn't a permanent sanctuary. It's just a momentary configuration in an endless cycle of galactic destruction and rebirth. Consider what this means for our cosmic perspective. For centuries, humans viewed the heavens as eternal and unchanging, a realm beyond time's reach. Ancient astronomers charted the same constellations we see today, their permanence offering comfort. But modern telescopes reveal a far more turbulent reality. The Andromeda galaxy isn't just approaching, it's proof that even our galaxy's current form has an expiration date. In 4 billion years, the familiar spiral we call home will be gone, reshaped into something new by forces beyond comprehension. This isn't destruction in the way we understand it. It's transformation on a scale that defies human notions of beginnings and endings. There's a humbling beauty in this impermanence. The atoms that make up our bodies were forged in stars born from earlier mergers, their explosions scattering the elements that would one day coalesce into planets and life. We're not just observers of this cosmic cycle, we're products of it, stardust momentarily arranged into consciousness. When images show distant galaxies twisted by collisions, we're not looking at some alien spectacle, but at the very process that made our existence possible. Those violent encounters enriched the universe with heavy elements, turned gas into stars, and sculpted the conditions for solar systems like ours to form. Yet this realization carries a paradox. The same mergers that create the building blocks of life also erase entire galactic landscapes. Countless civilizations, should they exist, may have risen and fallen in galaxies now consumed by ours, their histories lost to the cosmic tides. Our own fate mirrors this transience. Long before the sun dies, the Milky Way's merger with Andromeda will have altered our night sky beyond recognition, the familiar band of stars replaced by a glowing haze of alien suns. Future astronomers, if any remain, will gaze up at a sky where the word Milky Way is just a historical footnote, its meaning as lost to time as the names of ancient Earth constellations are to us. This cosmic ephemerality doesn't diminish our significance, it reframes it. Like surfers riding a wave, we exist in the brief moment where conditions allow for complexity, in the calm between galactic storms. Our ability to comprehend these vast timescales, to trace our origins back to stellar explosions and forward to galactic collisions, is perhaps the universe's most astonishing feat. The very fact that we can observe mergers unfolding across the cosmos, measure their consequences, and ponder our place within them suggests something extraordinary. The universe is not just a stage for matter, but for understanding. In the grand chaos of colliding galaxies, we've emerged as witnesses to the spectacle, our fleeting existence granting us front-row seats to the greatest show in the cosmos. Galactic mergers are the universe's great architects, silent, slow-motion collisions that rewrite the cosmic landscape over billions of years. These aren't just spectacular light shows. They're the engines of creation, forging new stars from chaos, awakening dormant black holes and sculpting galaxies into shapes we're still learning to classify. Every ripple of starlight, every twisted spiral arm, tells a story of gravitational encounters that shape the cosmos as we know it. And the most astonishing part, we're witnessing just a single frame of this epic film. The Andromeda galaxy barreling toward us, the ghostly trails of long-digested dwarf galaxies in the Milky Way's halo. These are threads in a tapestry of collisions that began with the first galaxies and will continue until the last stars fade. What's truly humbling is realizing how deeply interconnected these events are. The oxygen we breathe, the iron in our blood, even the gold in our jewelry, all were forged in the hearts of stars born during ancient galactic mergers. Those cataclysms didn't just rearrange cosmic real estate, they created the very elements that make life possible. When we study galaxies like the antennae or the mice, with their fireworks of newborn stars, we're not just observing distant phenomena. We're tracing our own origins back to collisions that happened billions of years before Earth existed. Yet for all we've uncovered, mergers still guard their secrets. Why do some galaxies emerge from collisions as elegant ellipticals while others become chaotic train wrecks? How do supermassive black holes find each other in the chaos and merge, rather than stalling forever? Every answer telescopes like JWST deliver brings new questions, reminding us that the universe's grandest transformations are still revealing their rules. So the next time you look up at the Milky Way's faint band across the night sky, remember, you're not seeing a permanent fixture but a snapshot in an ever-changing story. In billions of years, our descendants, or whatever inherits this corner of the cosmos, will gaze up at a completely different heavens, reshaped by the same forces that built the galaxies we know today. The universe doesn't stand still, and neither does our understanding of it. If these cosmic collisions fascinate you as much as they do us, let us know in the comments. What galactic mystery should we unravel next? Don't forget to like, subscribe, and join us as we keep exploring the universe's greatest transformation.